Are the AI systems that we're building today truly creative and intelligent in a way that exceeds human capabilities? There's evidence to suggest they are, but there's also evidence to suggest we're not quite there yet.
This is Deep, the show about the emerging deep technology that will change the world. Today I'm chatting with Michael Black, among the world's leaders in computer vision and artificial intelligence. He is the founding director of the Max Planck Institute for Intelligent Systems, where he leads the Perceiving Systems Department, and has co-founded two companies, Meshcapade and Body Labs, which was acquired by Amazon in 2017. Among Michael's many contributions to the field, he and his team created the Simple model for human behavior, a metric system for representing human bodies and movements that has become an industry standard. So why is the field of computer vision and AI making such remarkable strides? What will be the next breakthroughs? And which type of companies will lead the way? This is Ben Kaplan from Deep Venture Partners, and let's go deep.
Michael, welcome to the show.
Thanks for having me. It's a pleasure to be here.
We've chatted in the past. There's a little bit of a funny reason why Perceiving Systems is the department you had, but it's meant to be sort of computer vision in a little bit of a more general way. So maybe just bring us up to speed of sort of like where the state of art is that now. You've been working on 30 years, and why this is such an exciting time, and why this goes beyond OpenAI's ChatGPT in terms of potential of what AI can do.
As you mentioned, I've been working on this for about 30 years. I started in the Bay Area working at Xerox PARC, and back then, or even in the mid-'80s, the approach for training computers to understand the visual world was to write down rules manually and write down equations. And obviously machine learning has changed all that. And we're in a time of big data and large compute. And so now we train computers to understand images or videos by giving them lots of examples of images and videos with various kinds of labels associated with them. And then train generic algorithms to model the relationship between pixels, or the intensity changes in the visual world, and meaning. And so the game now, it used to be all mathematics, and now it's all about data. And so my research has changed a lot over the years, and now heavily leverages things like large language models and so on. And actually, one of the interesting surprises in the field of computer vision has been the role of language in helping to solve the vision problem. Many people, I think, including myself, would have thought that vision evolved in humans and in other animals long before language, right? And that we would, have to, that's sort of the easier problem, and we would solve that first. And that language, because it evolved late, would be hard, and it would, it would take much longer to get to language. But the flip thing happened, right? We kind of, I won't use the word solved, but we have these great models of language now.
It turns out language is sort of predictable. Like literally it is predicting the next word.
And maybe that's not surprising because we created it, right? So we created it and it's kind of mechanistic in that sense. And then it turned out that vision was actually the harder problem to really understand the visual world. And maybe that's not surprising, because we don't even have language for everything in the visual world, right? We only have language for a subset of the things out there. So vision is kind of a bigger problem. But the surprise is that language models are actually super helpful for solving the vision problem. You can think about it this way. It's very hard to imagine as a human what it means to read everything ever written by humans, right? In every language across human history. But that's effectively what a large language model can do. And in that, humans have described the visual world in all kinds of ways. And we've written books about physics and optics. And, a large language model effectively has access to a description of the visual understanding of humans. And through that is actually able to learn a tremendous amount about the visual world that we, as computer vision researchers, can then mine to actually solve this problem of converting camera images or pixels into meaning. And that, to me, has been the biggest surprise in my career.
To give a sense of sort of levels of difficulty of problems in computer vision, for people who don't know, and people may have encountered computer vision. They're starting to see it now because they're seeing this, car drive next to them and there's no one in the driver's seat, and they're seeing and doing this, and they have a sense that, okay, maybe that car is identifying like there's a person and there's a road and there's a light and here's another car, and to self-drive, it needs to do all of that. How difficult is that a problem to compare to where we are now and the work you're doing, where you're saying that, okay, we need the embodiment of like, and this gets into robotics, but like, let's say a robot, an entity that's going to interact in the physical world and interact with humans. How much harder of problem is that versus sort of the computer vision needed for a self-driving car?
90% of driving is pretty easy. Like, we let 16-year-olds drive. We often drive and get from one point to another and don't really even remember having done it. It's kind of a semi-autonomous task. And that's because we as humans have built the road networks and the signage and everything to be safe and easy to navigate without requiring a lot of cognitive load. And the reason that autonomous driving isn't solved yet is because there's still this small fraction of cases that I would call AI complete, that you really have to understand the visual world in a very deep way to basically do problem solving. I was once in a mountainous area of Germany where there's a lot of snow, and the road had been reduced basically to one lane in both directions, and people were parking all over the place because they wanted to go skiing. And effectively, we as a community made up the rules, right, for this weird one-lane situation. We weren't following any of the normal German driving rules, but it worked.
I'll give you an example for me in my travels. Maybe this would be sort of similar. In Vietnam, on a scooter or a motorcycle, I had some intersections where there was no discernible, me as an outsider, way of knowing. I mean, it was every direction going every which way, yet people who live there know how to do it. I was, holding on for dear life and trying to get through this intersection where there was no light, signs, rules, anything, but people kind of knew. There was context for it. This is something similar to what you're describing. It would be very hard for AI to navigate this.
And humans in those situations are communicating with each other, partly through, as you said, context or prior information. We know kind of how people are going to behave in certain situations. But when we get outside those situations, then we have to actually communicate through gestures of facial expressions and so on. So the sort of one of the complicated parts of driving is understanding what humans are going to do, not just in other cars, because they should, in general, follow the rules, but pedestrians, for example, or children in particular, or animals. Their trajectories in the world are not always easily predictable, and we're making judgments about them all the time. That's a kind of a form of communication, and it's all through body language, it's through movement. Again, our intuitions about what's easy and what's hard are not perfect. If we can label it, computer vision, modern machine learning methods for computer vision are good at it. I can label a lot of traffic signs, and this is what a green light looks like. This is what a stop sign looks like. This is a pickup truck looks like. And I give lots of examples, and then I can train an algorithm that's very good at, perfect at recognizing street signs. But human behaviors are much more complicated.
Is it because they're more nuanced or there's more complex? Like for instance, could you label a smirk? If I were to smirk right now, you could easily recognize that, but not that, but it's like I could do 10 things at once. A smirk with a, change of my eyes thinning with this means I'm making a joke. I'm not making a smirk like I don't agree with you. I'm actually making a joke and doing a fake smirk because I did these other things with it.
Absolutely. And you see this all the time. So there are large vision language models or multimodal large models that can take, for example, images in and produce text describing them. And the text is often pretty good, but in exactly the situation you're describing, you may get the wrong answer. And it's very common to get the wrong answer because you as a human will look at the whole scene and try and figure out a lot of the motives behind, why is the person making this facial expression? What else is happening in the environment? What could be going on? And those are still hard problems for AI systems. But the real issue with human behavior, so it all comes down to labels. So why is OpenAI so successful? They are obviously clever, and they have large models, but they're really very good at getting high quality data. They've taught us that scale matters. And we think about scale as number of GPUs or number of model parameters, but it's really about data. It's the size and quality of your data that matters. And that data isn't just raw numbers and things, it's labels. And those labels are usually provided by humans. And what humans are good at labeling, sort of, is things that have language associated with them. So I can label a street sign, I can label a stop sign because I've got a name for it. The problem with most human behavior is we don't have names for it. So say this. So whatever pose your body is in right now has no name. It's probably sitting, but if I ask you to describe precisely your facial muscles, the pose of your right shoulder, the bend of your index finger, there's no name for this, right? There are names for things like yoga poses. We have downward dog and warrior one and so on. And there's names for ballet poses. And we have names for all kinds of sports actions that we do. But most of what humans do in day-to-day life has no name. And it's because in the language of today, humans are a generative model of human motion. If I want to teach you to hold a golf club, I show you how to hold a golf club. If I want to teach you how to swing a golf club, I swing it and you watch me and then you try and mimic it. We have a name for golf swing, but exactly how to swing a golf club, you kind of have to do it. This means that most of human motion is kind of dark matter. We don't have a way to label it. And if we don't have a way to label it, we don't have a way today to train computers to really understand it. And I think this is why it's hard and interesting, and still computers don't really understand us fully.
If more than the majority of human communication is nonverbal, then we still have a long way to go. What is the state of the art there for that other 55% of communication? Like, what can we do now? What can't we do now? And is the lack of labeling truly the gap, or is it something else that's going to bridge that gap?
Yeah, as you mentioned, there are various estimates of how much human communication is verbal or versus nonverbal, and there are estimates that 55% of communication is nonverbal, which is kind of surprising. But it means that even if you're having the world's best AI conversation with a chat bot, you're still missing most of what it means to be human. And these kinds of communication are subtle things. We don't even really think about them, but you're walking down the hallway at work and you don't bump into your colleagues. You negotiate somehow through body language how to pass each other in the hallway, or you open the door for somebody. There's a nonverbal communication about who's going to go first and, so on. Or passing off a cup of coffee in the morning, bringing a cup of coffee to your spouse is like, you don't spill it all over the place because there's a nonverbal communication about making that handoff. And some of these things, one problem is not having labels for it, or not even knowing we should label it. And the second is that much of it is three-dimensional and very precise. So the handoff of that cup of coffee, if you tilt the cup just a little bit or fumble it, it will spill hot coffee all over you, which is a bad thing. What we really need are labels of human behavior that are metric, that is not purely semantic. So you mentioned a smirk. Okay, so that's a semantic label of a facial expression. But we need to be able to reproduce finger motion in 3D.
Like, you mean like a 17-degree vertical smirk with a
right.
depth component that's another metric with a 4% forward lip motion. We have to describe all of those things to be able to reproduce it.
And we're not good at that, right? So we're never going to do that with language. Language is just a bad way of labeling human behavior in 3 dimensions, or 4 dimensions if you consider time. And so we've been working on a technology called SMPL, or SMPL, and we call it SMPL, but it stands for Skinned Multi-Person Linear Model. And this is a very accurate 3-dimensional model of the human body, including all the soft tissue deformation, the facial motions, the motion of the fingers. And it's a 3-dimensional graphics model that we learn from literally hundreds of thousands or millions now of 3D scans of people. And we train this model to accurately represent human bodies and their movement. And this can be very, very compact. So the model has about 100 parameters. So that means there's 100 numbers that will describe your body shape, your facial expression, your body pose very precisely. So everything about you that's really kind of essential to your expression and your interaction with others, we can compress down into about 100 numbers. So we think of these 100 numbers as the label of human behavior. Because with that, I can recreate, your actions and behaviors super realistically. So that's what I think we need. We need this, a new language, if you will, of humans and their behavior so that we can then train AI systems to understand that language.
Michael, where are we in terms of applications, usage, how this can impact and sort of better our existence, human life in the near term? What's near term and what's further away?
There are many applications. Many would surprise you, potentially, of understanding 3D humans. I spun off a company from Max Planck many years ago called Body Labs, and that was commercializing this technology largely for the apparel industry. So if you want to design clothing, you want to design it around real 3D humans and their bodies. If you want to fit them into clothing, you need to know their body shape. So this is a metric problem. You have to understand the size and proportions of the body very precisely. So it seems like very different from what we were talking about with robotics or AI. But there are many other applications today in sports analytics, fitness, having a personal sports trainer that understands your movements and can demonstrate for you how to do things properly. In AI training, I talk about this simple body model, the parameters being a label for human motion. So it's super useful in AI training because what everyone's realizing is that for generative AI, particularly of images and video, to be really useful for creative people, they need more control. Language is not a very good mechanism for controlling such models. It's not precise. And animators need better tools, better precision. And so if you want to control the motion of a character precisely and have it do exactly what you want, you need to have the right labels. And I would argue these labels have to be 3D, like a simple model. And then there's video games. I think video games are going to change dramatically in the next few years. Right now, character behavior is captured using traditional mocap techniques. It's manually processed. Have a small number of actions the characters can do. Non-player characters tend to be very, very simplistic and driven by a simple set of rules. And all of this is going to change completely, I think. And games will be much more interactive in the sense that everyone will be experiencing it in a different way. The characters will have intelligence and be able to solve problems and interact with us in radically new ways. And this all means that they have to move naturally like real people. They have to understand how their movement achieves goals. And all of this requires basically 3D motion control and relating it to the environment and the actions of other agents in it. And this is all supported by the kind of technology we're developing. So an AR, VR, another major use case, if you're going to have AR glasses and put virtual agents in the world, they have to understand the actual 3D world that you're observing. So, you want a character to sit on your sofa, it has to see your sofa. It has to be able to move. It has to be able to interact with the 3D world, even though it's virtual. And so all of these use cases are very present. And we spun off a company called Meshcapade a few years ago that's commercializing this and has customers basically in all of these, just basically in all of these different vertical markets.
Are we going to see then sort of this division between this like very precise level of, I guess, artificial intelligence to interact in the 3D world, and then what you've called before artificial good enough intelligence, meaning there's a lot of things we don't need a lot of precision for. A good example would be a lot of things that people are using Chat GPT for now, right? Like, give me an outline for an essay I need to write on this and include this or that. And it generally has to be like passable, but it doesn't have to be Hemingway. Like, are we going to start seeing different types of tasks and is a big demarcation line 3D world and interacting in it and not? Does that become one of the big demarcation lines?
Yeah, I think it's, we all thinking about AGI and having an intelligence that's absolutely perfect. I think we have a new form of intelligence on the planet now, and it makes mistakes, but humans make mistakes. We make different kinds of mistakes, but we clearly have a new form of intelligence on the planet. But when we talk about agents interacting with us in real time, again, it doesn't have to be perfect, because when we're interacting, we're constantly correcting. Like, if I am telling you something and you're not understanding it, I'm observing your facial expressions and I'm realizing, oh, wait a second, he's not getting what I'm saying. Let me rephrase that, right? And so, when we have fully interactive systems, and they're coming now, and they're aware of us, then they don't have to be perfect. If I'm handing you that cup of coffee and we haven't got it quite right, we'll each correct, right? And that's how humans are, right? We don't. I don't close my eye. I don't see you, close my eyes, and then hand you a cup of coffee and expect it to be perfect. I expect it to be an interactive loop where I'm observing you, you're observing me. I kind of have a mental model of what you're going to do next. You're not going to wave your hand around in some crazy way because you're going to take the coffee, right? It's that effectively having a theory of mind and relating it to behavior. Now, I think existing AI models, large language models, are effectively have some kind of theory of mind. How deep, I don't know. But we need to relate that to 3D human behavior in the world to be really effective.
All of this begs the question, will AI become a commodity that's just like turning on the electricity? Back in the day, you might have cared about exactly who made the chip inside your computer. Hence, it was Intel inside. But these days, those same chips are mostly commodities. And is that what the future of AI looks like?
No, we're already seeing it, I think. People move very quickly from one AI platform to another if it's got better features, right? People track this, and I think loyalty to a particular platform may not be very high. And so I do see a commoditization of the core technology coming. And as you point out, I used to really care that I had an Intel processor in my computer because, Intel was ahead of everybody and they had a great marketing campaign about that. And now I have no idea, Apple's making I believe made the chip that's in my computer. Where was it made? I have no idea. I don't, it doesn't matter that much because it's reached a level of performance that's beyond what I actually need. And with many AI models, we're there where the performance is beyond what I need for the tasks I do, and therefore it doesn't matter which one I choose. And so what will happen though, why is Apple so successful? Well, it's not because they necessarily have a better processor, but they provide an overall better customer experience and maybe than somebody else. And somebody prefers the Apple customer experience and integration and so on. And so it's the standard thing. You got to know your customer. You got to know their needs. You got to service the customer needs better than anybody else. But with AI, I think there's an additional element that when the AIs become really personal and know a lot about me, I think I will get locked in. So if I've been talking to an AI for 5 years and it really knows how I think and can predict, it knows my schedule and it knows who I want to meet with and who I don't and what's important to me, there's huge value in that, right? And then switching is really hard. People get locked in. So I think we'll see commoditization in some sense, and then I think we'll see business models evolve around personalization, which will be critical.
Put on your investor's hat and to make sense of the companies and the landscape. And some are doing work on large language models. Others people are applying things to industries. Where do you focus your time and attention with your investor hat on?
I think, the answer is in real estate: location, location, location. It's really team, team, team. If you've got a great team of people, and that by great team, it has to include the right mix of clever technology people, as well as clever product and business people. If you've got that right mix, they will figure out, how to adapt. I worry about, if I were an investor, I would worry about pouring a lot of money into a heavy compute and data business where the competition there may be won by somebody with just a bit more compute and data. It becomes a bit of a race. I think right now there are many open source large models that are good enough that smart teams can start building really valuable products around them. Fine-tuning such models is not that expensive to do. And so you don't need to be pumping in hundreds of millions into a seed stage company to really begin developing interesting products that meet needs.
Like if you were coming from, and I focus on like sort of technology that's sort of trapped in academia that we can bring out, but it's easy to focus on like, oh, this technology is my life's work. We discovered some interesting things that are worthy of discovery. And now, what are all the applications I could think of for this? Oh, this seems like a good one. Let me do that. But that may not reflect the true customer need if you take that approach, is what you're saying.
Yeah. Yeah, the real risk here is also, of course, that the customer often doesn't know what they need, right? And particularly when it's a new technology that they've never heard of before, sometimes the customer need isn't there, and you have to invent that. And then that's expensive because you have to teach the world why it needs something, right? And the risk in that is always being too early, right? The world is not quite ready for it, or other pieces of the world have to come together. I think AR and VR AR is a particularly good example of this. I would be leery right now of developing, small companies that are selling into an AR market, or assuming there's going to be a big AR marketplace in the short term, because they can't control it, right? That will be controlled by some large device manufacturers, most likely. And you never want to take that kind of dependency. But I think there's a tremendous amount of really interesting hard problems that AI can now solve and make people's lives better. And it doesn't take ginormous amounts of investment to do that. It just takes the right kind of team that's nimble and focused.
You've said before about kind of adaptability being a skill in this, which is not necessarily something that they teach you in academic research, is to do that. And it's almost like academic risk-taking. Like if you see someone in their academic research that have kind of been follow the straight and narrow, it's always this path. But if you see someone who like jumps around a little bit and they seem to have broader interests, is that indicative of something that is more adaptability, that might be a good team member, or might be a good founder, or might be someone else that you could build more of a company around rather than just academic research?
Well, it's a great question, and I'll tell you the secret of academia. The successful academics, it's some combination of being absolutely stubborn and sticking to your guns and being willing to change. And I don't know the exact right combination, but every Nobel laureate will tell you the same story, that they had this idea and everyone thought they were crazy. They couldn't get funding. No one would hire them. They found the way to scrape it together, and they kept doing this, and they pushed this idea, and it changed the world, right? Every Nobel laureate has that story. That's a key, right? But you have to be right. So there are academics who continue doing the same thing they've always done for their whole careers, and it wasn't a Nobel Prize winning idea. So you have to know when you have to have that good taste to stick with an idea, and then also have the common sense to switch when, something better comes along.
Which sounds a lot like an entrepreneur as well.
It is.
You got to stick with it even where the world says you're ridiculous, but then you've got to be smart enough to realize when a pivot is needed in something else, and now you've got to change course.
To me, entrepreneurship and academia are very similar in the kinds of personalities and skill sets that are successful. There's a lot of risk-taking in academia. There's a lot of selling. We sell very differently as academics, right? It's a different medium, but it's really about having an an idea and communicating it. But not every academic's the same. And I have a philosophy as an academic, and it's very simple. And I tell my students this all the time. It's build what you need and use what you build. And if you do that, you're probably going to do well. And it's kind of the same thing in a startup. We tend to build things in my group because we need them and we're going to use them and they're going to advance our research. And then if that's true for us, it's probably true for other people. They probably also need it, right? And so then that turns out to be a successful strategy for choosing problems to work on. But it's also an example of eating your own dog food, right? If you built it and then it's like you don't even use it, probably nobody else is going to use it, right? So I think that philosophy works both in academia and in startups.
We've spent most of this conversation talking about the applications of understanding the 3D world and computer vision. But where do you see all of this knowledge sort of impacting adjacent scientific fields, scientific research? I mean, we see a lot now in academia where it's not purely, there used to be this divide of like, oh, are you, if you were in deep technology, are you life sciences or are you physical sciences? But techniques are crossing over. The solutions aren't so neat. So where do you think this is going for, like, besides fields like robotics, where it's very, very clear that there's sort of an application, but what about other types of fields where you think, sort of next generation AI, machine learning, understanding of the 3D world can impact totally different fields in ways that might accelerate discovery?
It's a great question, and one I think about because I do enjoy, we talked about video games and robotics and all kinds of things. I find them very exciting, but I also want the work we do to have a broader impact, and particularly on human health. We work on a bunch of problems in that space related to eating disorders like anorexia nervosa, obesity, cardiovascular health, cerebral palsy in infants, biomechanical, sports injury related things. And we're trying to make the technology accessible enough to practitioners in those domains that they can use it. So, for example, we work with psychologists who use our 3D human model, the simple model, to work with anorexics. One of the things they used the model for was to challenge a notion that had been prevalent for a while, that anorexia was a disease of perception, that people just saw their bodies as heavier than they were. They incorrectly perceived their body size. And that then people were developing therapies around that notion. But using virtual reality and 3D body models of the people, we could vary their size, right? And vary the size of other people, themselves and others, and showed that anorexics actually see their bodies and the bodies of others veridically. That is, they see them with metric accuracy. So they're not biased in their perception, but they were biased in their preference for body shapes that were unhealthy. And so then this allowed a whole new, cut off an area of research and opened up new ones for how to treat anorexia through virtual reality experiments with 3D bodies. So, but to get there, you have to make the technology accessible. It's not enough to just have a GitHub page and put your code up there and expect psychologists to be able to figure out how to install it and use it. You have to build infrastructure around it. You have to build effectively a product around it to make it accessible. And one place I see AI accelerating that is in helping create interfaces that are easy for, say, lay people or specialists in another area to use this kind of technology. Programming is changing incredibly quickly, and AI systems are accelerating that at a mind-boggling pace. And so I think that it will be much easier to take technology like ours, developed in one application area, and then transfer it to other ones where you need different domain expertise.
Which also seems to be another, to put the investor hat on again, opportunity for investment, where certainly you could apply it to a particular area, but in some ways it's opening it up so that other people can apply it in other areas. Might have great potential impact. And if it has great potential impact, it's valuable. If it's valuable, you probably have a valuable company.
Yeah. So one of the things we've been doing at Meshcapade, we created this simple body model at Max Planck, and then Meshcapade has been licensing it, and numerous academics are building around it. And it's effectively become a de facto standard for how you represent a 3D human. And the advantage of having something that's a standard is that everybody starts developing around it. You've got academics, you've got startups, you've got big companies investing in that. And that creates an ecosystem where there's a lot of synergy and simultaneously experimentation all over the place. Like everybody's trying out different things. And then you can, as a community, figure out, well, what works and what's really the best way forward. So getting everybody on board with something that's standardized really helps with this, creating an ecosystem in which many kinds of startups can emerge, solving different problems.
The final thing I want to ask you about, Michael, is just whether this holds true, because I mean, you're unique in that I think you consider yourself an academic primarily, but you have done things in the sort of commercial world and with companies and all of that. Do you think it's still true, this idea of one of the big advantages of technology that emerges from a university is you can get a lot of grant money, support, without the sort of the pressure of commercialization yet. Essentially, you can stay sort of spun in until you're ready to spin out. Do you think that still holds true, that universities are a great incubator of sort of technology and scientific discovery and ideas and all of that? But then what makes it so great also makes it difficult to get it out because it's not in this commercial environment. Do you still think that holds true? Is it still stay spun in until you're ready to spin out? Or is it a little bit different now? Might there be more opportunities to maybe spin out a little earlier and continue doing research that might otherwise be inside a university?
Great question. The answer varies, of course, right? And it depends on risk and time needed to develop the technology, as well as what the sort of competitive landscape look like. But in many cases, I do advise startups to stay spun in because that's effectively a non-diluting investment. Any sort of research funding you get is non-diluting, in the sense that your academic institution will probably take some fixed percentage of your company when you spin out. And it kind of doesn't matter how long you stay spun in, they're still going to take that percentage. It really is a kind of a fixed amount. So that can be exactly the right thing, particularly for teams that don't already have a business person. This is a big problem for academics. They're often, all of their friends are academics, and they just don't know people who have business development, product experience, and so on. So that gives you time to make that network and build it and then spin out with a strong team. On the other hand, some things require today more funding than is possible to get in academia.
In my work as an investor, I focus on technology that is trapped in academia that we can bring out. And the issue is, sometimes a technology is someone's life work. And when it's your life work, you want to find every potential application for it. But at the same time, could it be better to put the customer hat on and say, what are the problems we need to solve first? And then what technologies can help us solve those problems?
Yeah, this is an issue for most academics. I'm a little fortunate at Max Planck. I have a very flexible research budget, and I have a software engineering team and a data team, and we can push stuff a little bit further than it. It's very hard to fund this in many academic institutions, particularly in the US. So you're absolutely right. Today, in computer science and AI in particular, we're always getting stuff out to people. It's not enough today to write a paper, publish it, sit back and pat yourself on the back, right? If you don't have it on GitHub, and if you don't have it on Hugging Face, and if you don't have a demo out there that people can actually use, your stuff is not going to get very much attention. And so people are building sort of pre-products in some sense to get traction.
So it sounds like very much like the ChatGPT story, right? It's just like great publicity, PR that just propels you ahead.
Yeah, and that happens in academia. It really is. The world is really changing, and the standard academic publishing model
at least, in some fields, I'm sure it hasn't changed much, but in AI related fields, it's changed dramatically. And it is much closer to something that is productizable, even when it's still in academia.
Final question for you, Michael. Just, do you think like the next 20 years of human history, I mean, will this surpass in terms of our understanding development the prior 100 years? Do you think will it be more than that? What do you expect next from the next 20 years of what we're able to accomplish as humans, as humanity?
Fascinating question. It sort of rests on a key thing. Are the AI systems that we're building today truly creative and intelligent in a way that exceeds human capabilities, or at least matches them? There's evidence to suggest they are, but there's also evidence to suggest we're not quite there yet. But when we have machines that are more creative, and I'm using the term creativity here because it's a key piece of this. It's not enough to know every fact in the world and be able to synthesize it in interesting new ways. But true creativity, thinking outside the box and coming up with problems and solutions that no one's ever thought of before, this is the hallmark of human intelligence that drives society and science forward, right? And if we've built systems, artificial systems that match or exceed that, then there has to be an acceleration of technological progress. Now, I think over the next 20 years, I think that's highly likely, right? I think over the next shorter than 20 years, this is highly likely. And I think the big issue then is matching huge advances in technical progress with the societal changes necessary to accept that without causing mass dislocation.
We need the technologists, but maybe we also need the politicians and the sociologists and everyone else to come together. So thank you so much, Michael Black, for joining us on Deep.
You're most welcome. Thanks for having me.
This episode has been brought to you by Deep Venture Partners. Get show notes, transcripts, helpful links, and more at deepvp.com.